Alright, so this is my second video for the review for your test tomorrow. I recommend that you study this particular bell work that I gave you, in which we basically we talk about certain techniques of taking derivatives that we studied during the this whole chapter. So it is important right here. This I'm going to ask you. I'm telling you. I'm going to ask you that you know the limit definition of the derivative, and that you keep in mind the notation, such as the limit as h approaches 0, f of x plus h minus f of x over h, and apply this definition, the limit definition, to whatever function I'm giving you. So I'll be checking for this particular notation and whether you keep track of your limit as h approaches 0. The other ones that I'm going to ask you is basically any of these: sine, cosine, tangent, secant, cosecant, cotangent, trigonometric functions. But what I have noticed though is that a lot of you guys already feel comfortable with sine, cosine, tangent, but when it comes to basically secant, cosecant, cotangent, sometimes you're not there 100%. So my job will be now to ask you derivatives in terms of any of these three pink circles, trigonometric functions. And keep in mind that whenever we deal with cosine, cosecant, cotangent, we have a negative sign in front of it. Now, the other thing that I noticed though was, based on your multiple choice test, that when it comes to secant or cosecant x, cotangent x, and there is something else in the argument. Let's say you have 2x, and I ask you to take the derivative. That's another way of writing derivative. Secant 2x quantity prime. A lot of you guys are writing secant x, tangent x, because basically that's what the definition says. But in reality, this x right here, that x right there, is the argument of your secant. And that argument can be anything. It can be 2x, it can be 9x squared, it can be 10x to the third, whatever it is given. So when you take the derivative, you basically take with you the argument that is given in the original function, like in this particular case. So rewrite it. Secant, this 2 is very important. Make sure you know the distinction between when 2 is secant square versus when the 2 is for the argument. So rewrite 3x quantity squared, the 2 belongs to the argument, that's 9x squared. So now as you can see, the argument here, it is no longer x, it's 9x squared. So when you take the derivative, you're going to see 9x squared. So dy dx is going to be, the derivative is going to be secant the argument, take it with you, tangent 9x squared. Now I've taken care of the derivative. Now the derivative of the argument by chain rule, 9x squared is 18x. All right, and rewrite. Make sure you pay attention to that. Rewrite it. When you subtract -1, make sure you know what is left. Take the derivative, chain rule. This right here is very important because I want to know whether you're able to apply all the rules that we have learned. In this case, we have 3 altogether: quotient rule, product rule, chain rule, all at the same time. So you got to keep track of everything. And something very important is, I want you to write everything in simplest form. So be careful. In this one, product rule. So make sure you keep track of your product rule. All right, now what I want to also review is, what if I ask you, vertical tangent lines. Let's say I give you implicit differentiation in which you get, I don't know, 2x minus 3, I don't know, y square minus 1. And I ask you to find the coordinates in which the curve, the curve that you're given here is going to be something here, has a horizontal tangent line or a vertical tangent line. Okay? So based on this, if I want to find horizontal tangent lines, I know that the derivative has to equal 0. So you take the derivative and set it equal to 0. But something that you're going to realize is that basically you just end up with 2x minus 3. Because when you do y squared minus 1 and this is 0, y squared minus 1, this basically reduces, and therefore you just end up with a numerator. And to find the horizontal tangent lines, in this case, just set the numerator equal to 0, and you'll be able to find the x coordinate. So at 3, 2x equals 3, so x equals 3 halves. But since I want coordinates, this is 3 halves, I need to find my y coordinate. And what you do is you place it, you plug it in into the original function that you're given, or whatever is given to you. If I ask for a vertical tangent line, we know that a vertical tangent line has an undefined slope. And so in this particular expression that I gave you, dy dx, you have 2x minus 3, y squared minus 1. Then I want to find what particular values will make this particular derivative undefined. And so in order to make it undefined, we know that we cannot divide by 0. So you take whatever is in the denominator and you set it equal to 0. So y squared equals 1. In this case, y is plus or minus 1. So in this case, I have 2 points. One is y positive, one is negative. And so, but I still want to find the x values. And again, you take 1, plug it into the original function, take -1, plug it into the original function, and you'll be able to find the coordinates of your points where the curve that you're given has a vertical tangent line. All right, next. Let's say we have particle motion. And I'm going to ask you to basically find the velocity function and also the acceleration function. And you're going to start with the position function. In this case, let's say I give you -2 cosine of 3t squared. So let's say I give you this. Well, v of t, and again, whatever notation you use is fine. V of t is going to be the derivative of your position function. So -2. The derivative of cosine is negative sine argument times 6t. Okay? Negative times a negative is positive. 2 times 6t, that gives you 12t sine 3t squared. If I ask you for the acceleration function, now I know that it's going to be the derivative of your velocity function. But now I know that I have two functions multiplying, so I have to use the product rule. So, f prime g, g prime f, whichever order you follow, just keep track of your product rule. So a prime of t is going to give me basically, I don't know, 12 sine 3t squared plus 12t cosine 3t squared times the derivative of the argument, 6t. Simplify this, you have 12 sine 3t squared plus 72t squared cosine 3t squared. Okay? So that is the acceleration function. But now let's say I ask you to evaluate this, to evaluate the velocity and acceleration, let's say at time t equals 2. So I want to know what is v of 2. So I know that I have to do 12 times 2 sine 3 2 squared which is 24 sine of 12. And so, or here, it's going to be a of 2, 12 sine of 3, 2 square, plus 72 times 2 square, cosine of 3, 2 square, which is basically a of 2 is 12 sine of 12 plus 4 times 72, 288, cosine of 12. And you can basically use your graphing calculator to evaluate this. But the idea is, you gotta be ahead of the game now. You should know how to use your graphing calculator in a better understanding. So here we go. So let's say this is a multiple choice, or even this problem. You can follow these steps. So since I'm using the graphing calculator, and you're allowed to use the graphing calculator, go ahead and use it. Take advantage of this graphing calculator. A lot of you guys on the multiple choice test, some of the questions, the last 3, I asked you to use a graphing calculator, but some of you guys didn't use it, and therefore you couldn't get the answer. All right, now let's say I want to evaluate the derivative, my velocity function, v of t at t equals 2. All right, so what we do then is I'm losing my screen, and that's not good. I hate this, and I don't know. So here we go. Let's see. Let's go back now. So let's say I want to evaluate the velocity function at t equals 2. So the first thing you got to do is you enter your original position function. In this case, it's -2 cosine of 3t squared, but we don't have t, so we use x, close parentheses. That is your position function. Y sub 2 is going to be my velocity function, which is going to be the derivative of your position function. And so what I do then is I'm going to say math 8, the derivative of y sub 1 with respect to x, y sub 1 alpha trace y sub 1, not there, right here, alpha trace y sub 1, and then with respect to x at any given x. So that's one way. So what I'm going to do now is I'm going to go to home screen, and I'm going to evaluate my velocity function. But I know that the velocity function is right here, is my y sub 2. So you got to be careful what y you select in order to evaluate. So since I want the velocity evaluated at t equals 2, I'm going to use y sub 2. So again, alpha trace y sub 2 and evaluate it when time equals 2. And we get that the velocity value at t equals 2 is -12.87. So now that's my value of my velocity. So now I want to evaluate the acceleration. And the acceleration is basically the second derivative of your position function, or the derivative of your velocity. So since I already have here y sub 2 represents velocity, and I'm already here on the home screen, what I can do is math 8, take the derivative with respect to x in this case, but now I want the derivative of y sub 2, because y sub 2 already represents the velocity function. So I'm going to say alpha trace y sub 2.